real-time fast Fourier transform. And what we're looking at is the broadcast FM radio bands. This is like the commercial broadcast, maybe 92 megahertz or something like that. To give you a little overview, just so you know what we're looking at, we're running with some hardware that's got a PCI card in it with wireless running. We borrowed a desktop machine to put it in. It's 20 million samples per second, and we sample it to the FFT equipment. So that's what we got right now. So with that, we can go on and do some other tricks. Okay. So the first thing we want to make sure is that when people hear radio, or software radio, or GNU radio, we're not just talking about your average everyday, what people think of as radio, like the thing you listen to in your car. We're really talking about the most expansive definition of radio, including everything in the RF spectrum. So that includes things like TV, cellular, wireless internet, ad hoc mesh network, your remote garage door opener, car access, all of those things. When we say radio, we mean radio in the big picture.
We're not in
don't forget to run the radio.
We'll just do that.
We're not internet radios, I think this is streaming audio to run talk, but this could be used as a receiver if you were something line. And finally, what software radio is about in the most general sense is that we're trying to turn what have traditionally been hardware problems. Any of you picked up a soldering iron and tried to build a radio, but it's kind of painful. And we're trying to get around that problem and to be able to enable people to really hack radio. So we're building a whole system, and we've got a pretty good system in place right now that allows us to turn what were traditionally hardware problems into software problems. So the game plan, in the ideal universe, we want to get the software marched up as close to the antenna as it's feasible. And currently that's limited by the performance of the analog to digital converters and the digital to analog converters. So it turns out you can get pretty close right now, and things get pretty interesting. You start doing it more than one thing at a time. You get this incredible benefit that your radio, what it's doing is just dependent on what code is running in. So we can imagine a future not too far out where instead of people carrying cell phones that are like the second-class citizens of the network, a base station, that people are carrying these mobile communication devices which on the fly generate the entire network. And then you can figure depending on where you are. So, I want wireless internet access. Okay, well, how can I get it? And you've got some selection criteria. Well, let me go see if I've got free 802.11 access. Okay, good. Got that? No, don't have that. Do I have GPRS? Oh, maybe not in the middle of the Atlantic, so I need a satellite. I need to reconfigure the satellite. Or I want to know where I am, so GPS. And of course, there's still some on the actual analog electronics, so the very front end of the game, there's some kind of RF transverter, typically. The up converts it, down converts. But there's great strides being made in that area about making new things possible. So we're being able to build wider bandwidth radios. From speaking from my point of view as a software guy, not instance a hardware guy, I can tell you that. We really don't care. We've got some interesting other characteristics of the channel. What does it make possible? Mostly we take a first shot at it.
Sorry, if you're not implying that exists due to that base station.
You can do, it is possible.
Please repeat the question.
Greg, okay, the question is, it was the accusation that you aren't implying that you could do without an infrastructure like cell phones now, are you? I thought I asked a very good cell phone guy here, and they said no, so we found him. He works for the operator. No. Yeah, okay, good.
Okay, well, you can do the whole cell base station in software radio too, or I think more of what Eric was saying is that you could create some other network that you could use it like as a cell phone. It wouldn't necessarily be GSM. You could have your own ad hoc networks or whatever form.
Matt's going to be modest. He's done a lot of work in actually modeling these networks. There's some interesting data that says that you can continue to, as you add nodes to the radio network, that the aggregate capacity of the network continues to drop. And that isn't how people traditionally thought about radios. When you think about radios like TV transmitters, or there can only be one on a station, and then you put one more on and that, like, it's less and less people are able to communicate. Well, it turns out there's some great experiments being done in theory that say as you continue to add nodes, that the capacity of the network continues to increase. So, and that's some fun stuff coming.
Current implementations, for example, software-defined radios.
Can we get lights too? So we love the conversation.
I'll just boost the volume.
No, I think whatever. If I boost it up, because it's speaking back to me. Okay.
1 minute.
So in the current
implementation of software-defined radios, the equipment still uses traditional radio setup. We've got a number of fixed stations, and then the mobile units communicate through the infrastructure to these fixed stations and links.
is that back up? I don't want to try to repeat the whole thing. It's a great question.
Okay, in the current, I mean, the idea is great, and this is what's happening right now. But in all the applications that currently exist and are even being planned for software-defined radios, the traditional structure of having a network with open standard linking, still remains the case that the mobile units communicate with each other across this infrastructure.
That's fine. I mean, it's orthogonal to the issue of whether your radios were built as software radios or conventional, ESP-based fixed function radios.
Yes. I mean, the main advantage of these is that you can switch.
What about the microphone?
You can switch waveforms as you like. It's all software defined. It's not hardware design. So, the configuration of the radio can be, it's just a matter of switching software. The detection of the waveforms is all software. It can be done on the fly.
The software radio you kind of see as an enabler to allow you to deploy these more complex systems where there's no infrastructure necessary. You can adapt to different types of infrastructure. So the software radio, it's not necessarily necessary for that sort of thing, but it's an enabler. And but its primary advantage is really flexibility. That you can do just about anything with it. Just like you said, changing the software.
Good. Is there anything, anybody specifically questions or anything at this point, or is anything you want to make sure that we cover? We'll go do some demos along the way. They're probably not going to do much theory. We're the 10 people want to talk gory details. Okay, here's my favorite. This is the big picture of software radio. So we've got an antenna on the left. We've got some kind of RF transverter. And we just need those pesky things because our ADD converters aren't good enough yet. No, it's not really true, but it's kind of like that. That's the thing that does an up conversion or down conversion. So we'll come back to that. The next box over has got our analog to digital converters and digital to analog converters. Today, just to give you an idea of what you can purchase, for example, analog devices pretty much owns this business, is you can buy analog to digital converters that will do about 80 million samples per second at 14 bits. On the D to A side, the digital to analog conversion, they'll do 16 bits on the high end, 14 to 16 bits on the high end, up to 500 megahertz. So what that starts meaning is that based on the Nyquist criteria, you need twice as many samples per second as you have bandwidth of interest. So you start being able to grab with your RF front end and really huge chunks of the RF spectrum. So it enables things like in a cell phone base station, how they're doing it these days, is that grab the whole big chunk with one RF front end and then slice it all up in software. The RF transfer is required because we really, let's say that we can grab, say 20 megahertz pieces of spectrum, but we want to be able to figure out which 20 megahertz pieces of spectrum we're interested in. So I want one that's down at 10 megahertz, or I want one up that's at like 2.4 gigahertz or up into 5.1, or maybe we would want to build a microwave relay like we're using to get the wireless thing here, which is 5 or 10 gigahertz. I'm not sure that's actually familiar. And then, of course, the big bar, circle ellipse on the side is there's lots of software. So, again, it's the flexibility we're looking for, and then really the ability to rapidly build things. It changes as people have built hardware before. Hardware has this pesky habit of being, there's lead times for it. You decide you want to build something, you got to order some parts, and then there's always a part that takes 19 weeks. Okay, good, see you in 19 weeks. It's a little different than let's just edit the code, that's make, and load my new code, and all that stuff.
Okay. So right now, GNU Radio code is in a state where we can do basically all the standard analog modulation systems that we expect, like FM radio, AM radio, television. We've done American digital TV. Pretty much all the infrastructure is there to create the European DVB standard. Now, HDTV is not real time yet, but as soon as Intel, catches up, and there's we'll be expanding towards some things like satellite reception, GPS. All the building blocks are really there. You can do just about any modulation system that you can really imagine and would be used in radio. You can do in software. I mean, at the very least, if you think of it as just modeling the equations, that are used in the analog circuitry. Now, obviously, that's not the most efficient, but certainly you can do any modeling system that you want.
Great. And this is kind of in general we're talking about. Yeah. Go, you be talking about it.
You just have two pieces of hardware, and then you can scan all the sequences.
Well, this is what's up here is mostly kind of think of it as what's possible with software radio. So there's a second issue, which is what's the RF front end that I need to be effective in a given band. So I probably can't cover all of that unless I go with it. I can cover all of it with a very expensive RF front end. Because, for example, in that depends on if the satellite's up in the gigahertz range or if it's a couple of gigahertz. But yeah, it's a question of typically people are going to build something, at least in today's market, that will cover maybe a span of 2 gigahertz.
Like you only have, you generally won't have one device for most of the frequencies.
Sorry, what's the question? Just repeat
You don't
this.
have one device for a multitude of frequencies.
Yeah, for a given range. And again, it's a question of how much money you want to spend. Because there are some really spectacular radios that are really expensive and will cover a really wide range. Like an extreme example is an HD spectrum analyzer will cover from pretty much DC to about 26 gigahertz, but they're $50,000. So, it's like how much you want to spend. So, and if you think about how they're built on the inside, is they're really built as a very sophisticated kind of like a whole bunch of radios that kind of gets in there. The other thing we want to point out is that the software radio, it really is about whatever you can imagine you can build. From my point of view, is it's got the same kind of sense of attraction or the sense of possibility that I first discovered in working with software in general. Is that you've got the situation where if you've got a vision for it, there's really nothing between you and getting it done except your ability to manage complexity and maybe some computational resources. But if you're willing to kind of set aside real time requirement, there's nothing to stop you from modeling the whole thing. And they come up with things. Sure, question?
Then also the push forward in software radio by virtually new digital standards.
Can you hold the mic a little closer?
Didn't write the money out. It's an A range,
Right.
but they did the whole system and BSC outputs. I agree with that because I think that this would really push the technology of the software radio because technology has gone up.
Right. And the question is about the DRM system, radio, who we are. And technically it's a very narrow, relatively narrow band radio signal. It's digital. And there are some people on our mailing list that have talked about it. We don't get it in America, so it's unlikely that we would have allowed to implement it. We'd be delighted to assist anyone who would like to. We'll give you all, answer questions, we'll point you to building blocks, we'll give you suggestions. But it's an ideal application. In fact, it's really narrow band, and people were actually, that we're talking about, is do it using the regular sound card on PC as an analog I/O.
I believe that someone has actually released an open source spin-on for that already. It's not affiliated with radio, but certainly it's quite feasible on current hardware.
Sure, go ahead.
Don, I'm sorry, I may have misunderstood you. Did you say anything that you can imagine with sufficient intelligence you can achieve in the software, but provided you're willing to give away something, such as real time? Did I do that correctly?
Well, it all depends on your application. Here's the thing, but I'm absolutely straight about this. The computers get faster every year, and I don't have to spend any money to do it.
Sure.
Okay? Field programmable gate arrays are getting faster and cheaper every year, and I don't have to do anything about it. So I am free to present
programming.
But here's the thing, if I pick a good architecture and I don't tie myself down to some machine learning or some wacky DSP, I get to ride this curve for free. So if you look at you look at the people who built sort of if you look at the history of computer science and the really cool stuff, people did stuff that you would think, God, that was impossible. They had to build special hardware to run it. I mean, one of the things is these list machines sitting over in the next 10 over. I mean, come on, those were $150,000 each when they were new. They were personal computers, okay? So you got to kind of set the picture aside. We can press on with the software. The hardware's going to be cheaper.
Well, it's not just a question of that. I mean, if you're going to build a radio that people are going to buy, you're going to use some sort of radio standard. You'll use a communications protocol. Now, all of them are going to have real-time constraints. Tetris, for example.
Tetris is no problem. It's the narrow band stuff is easy to do. Real time. Where we're talking about problems with real time, for example, digital television. Seriously, we've been down this path. Sure. Digital television, the symbol rate is 10 million symbols per second. Tetris running 30 kilohertz? No. Okay, so
but for electronic radio, I mean, the problem is in order for radio manufacturers, they've got to make a product that's small enough to hold somebody's hand, that's cheap enough for them to afford, and that doesn't run so fast that it chews up the battery.
Okay, so all right. Okay, so this is a question that I throw in the category of why would I spend the money on this software stuff? Okay, I think I'll get your concern. Look, if you want to build a single function device, it's always going to be sufficient volume. You're always going to be cheaper hitting one target design. Now, you throw out pretty much all the flexibility in that. Now, where I go with this, and with regard to, at this point in the game, the generally programmable hardware consumes more power than ASICs. It's been that way forever. It's probably going to continue to be that way. Now, there are lots of companies, including Intel, that are doing a lot of work with these things called, they're basically mesh hardware that has heterogeneous processing elements on it. And where they're headed with this is really different than like radio in every processor. And they're very interested in power consumption. And as long as our minutes per watt continues to increase, at a certain point, I don't care if my mobile unit is using more power. My reprogrammable mobile unit is using more power than the dedicated ASIC, as long as I don't have to charge it more than once a day. So again, it's a curve. We're not saying that this is the only answer. I mean, look, we're going to do a demo here that's going to be the world's most expensive FM radio. We don't hold that here. We're not kidding anybody, okay? But we're inviting you to kind of expand one's point of view. We're not saying this is the commercial answer that's going to be really tiny and really cheap right now. But we are saying this is an amazing tool for innovation, rapid development, and being able to try new stuff out without having to ask anybody.
Also, I think, while we're not concerned directly with commercialization, I think where software radio is being commercialized first is in things like base stations. For example, you can, remotely upgrade your base station from GSM to GPRS, for example, by sending it software over the net. And that's certainly where it's going first, but there's a company involved in this area, which actually the same people created the source code that GNU Radio evolved from. And they recently downloaded a little module that plugs in the back of a Hanscom advisor, I think it was. iPad. It has a little bus in it. They have this little module that was basically just DA, and they used the strong arm processor that's in it, and they demodulated narrowband FM and using police station. And they also use APCO 25, which is like the US version of Tetra. And so they were able to do this on a handheld device. Now, yes, it consumes more power than any device they would have done, but they could switch back and forth between these things. So it is really a flexibility. Okay, pressing on. Well, look at that. Okay, so what else can you use? This is a thing we probably always said. This whole point that we can build radios that have never been built before. And we're not kidding. This is like, we're inviting people, and what happens when you start looking at this stuff is that at a certain point in this radio game, the communication system, all the modulation strategies and all is important, but it all starts looking like any other communications protocol. So you end up with some big stack, you end up with a big routing problem, you got all kinds of things. Part of what we're interested in is enabling a bunch of folks to come experiment in this area and see what they can create. So not everybody needs to know the guts of a particular modulation strategy. I was approached by a computer science professor in the United States about a week ago. And he's not an electrical engineer. In fact, it kind of scares me. He doesn't know much about it. And he's like, I'm starting the GNU Radio, software radio club, and we're going to figure out how to deploy an ad hoc network in the dorm. So I'm like, okay, great, more power to you. Now, do you have a friend in like an engineering department? But we're having this to make it easy. You got to set up just really, when you start thinking about taking your network guys, the protocol designers, you can start figuring out, well, what's a better way to route these things? Or, we see wireless internet today, 802.11. Great thing, it's doing a pretty good job of what it's designed to do, which is pretty much a wired replacement. But it was never designed to really put a whole pile of machines and systems in one place, or to not interfere with each other. So it's been one piece off.
Yeah, I was also going to say that this business about building radios that no one's ever built before, the original radio modulation schemes, AM, FM, things like that, were all designed the way they were designed because they had to be decoded in hardware and they had to be decoded in cheap hardware, so it would fit in a $10 in your pocket AM radio. But the result was they wasted a lot of bandwidth and they wasted a lot of capabilities that, FM came along X years later and was higher fidelity and it's stereo, wow. And then, beyond that they came up with sideband modulation so you could push twice as much stuff through, and then you got to, work your way up to digital modes and spread spectrum and further ways to slice up the spectrum in more innovative ways, to let more people share it, send more data through, etc. By the time you slice up the spectrum into bit samples in a computer, you can apply any kind of transformation that your mathematician friends can think of, or that your 13-year-old son can suggest, and try it, and see how well it works. And if it works better than the stuff people are using, then it'll get picked up. And that's sort of what we're here for. Great.
Do you have questions about, what can I do with this? And the next point is kind of one that's provocative. Anything software can do, you can do with radio. And what we mean by that is this whole thing about if you wanted to build the super TiVo or personal digital recorder kind of thing, well, once you've got this fixed-rate company, you're free to do whatever you want. Or ship it across the net, or whatever. We're not presupposing we have all the answers, but we like the idea that we really give people access to the stuff, and then you're free to do whatever you want. Make up an application. One of the things that's kind of interesting is if you start looking at digital television, you look at what's in the race. TiVo, people know TiVo, I don't know if it's your replay TV. So they record either satellite or terrestrial broadcast data, and since most, television, thank you. And they MPEG encode it, and they write it to disk drive. And then maybe you got some search function or something, or some I'll record all your favorite shows. And then you can play them back, and maybe you can skip the commercials, or maybe not, depending on what manufacturer you bought, and what their position on this is, and whether you discontinue with jumps forward, or you have fast forward to the explicit commercial, or it's going by faster. So all those things are possible. The other thing is with digital television, the job is really easy because the output of the receiver is actually an already pre-compressed transport stream. You haven't had data, so you just got to put it in the disk and store it up, and then you can actually look at the rolls and how the TV guide and comes along and figure out what you want to do. We get kind of a what's new slide here because some of you have heard us talk before. We've been at this for a couple of years now. And that went down.
Okay. So one of the interesting developments lately is a ham radio operator in the States has put together a radio that will do anything from 0 to 60 megahertz. So all the HF bands and 6 meter band. And what's nice about this is that it's all there for you. It's not the most complicated device in the world, but it's convenient in that it translates all that down to frequencies that the sound card can use and back up. So this takes the function of the RF transverter and also the amps and the monitor and stuff. And so that's this device that I'm speaking about. And it uses your sound card as the AD and DA blocks from that diagram before with the 3 blocks in it. The AD and DA is what's in every computer these days is your sound card. And so that kind of limits your bandwidth. You can only really look at about 40 kilohertz at a time. But it's a nice low-cost way to get into it. And certainly anything at 40 kilohertz you can do with a pretty slow processor these days. So this for ham radio operators, this is an interesting device, and you can do basically your HF and 6 meter radio. And we're working on software, front-end software, to make a nice ham radio-like system. And so next up is actually what you can see on the screen. This is a card that we've designed to do very, very wideband stuff. So this is the idea is that you can connect this to your USB 2 enabled computer, so it gets 400 megabits per second or so in and out of your PC. And this board will do the AD and DA conversion for you. And so it doesn't do the RF transverter type stuff, but it has the AD functionality in it. And what it has on here, it has each channel is a 60 megahertz AD converter and a 60 megasample per second AD converter and 120 megasample per second DA converter. So that, and those are 12 and 14 bits respectively. And so that's each channel. We actually have 4 channels on this board. So you can do, the idea is you can do smart antennas, you can do multiple input, multiple output things. Basically, it's a really nice test bed for just about any modulation system that is possible with today's technology. They all pretty much fit in that kind of bandwidth. So what's on here is a USB 2 chip and an FPGA, which does some of the digital up and down conversion, decimation filtering, and the AD and DA converters. I'm sorry? Yes. The source code, I wrote it, and the source code for it will be available when the board is available for sale, which will hopefully be in a couple of months. And the tools actually programming Altera come from Altera, and those aren't free. I mean, they're free, and you can get them and not pay money, but they're not free. And the good ones you have to pay money. But But anyone would be able to program that if they have the skills. The idea is that we will provide very simple, not very simple, but very flexible code for the Altera, which will do the up and down conversion for anything that you're likely to want, and you would do all the waveform specific and really interesting stuff in software. So the actual FPGA really just kind of does the bus interface and frequency translation, sample conversion, stuff like that. Although you could do more complex stuff. So the idea is that these boards will be available relatively soon, and the 2-channel version will be $300. So this is pretty compelling technology to get to that kind of price. We know of nothing in that league for that kind of price. As an example, there's a company called SCS that, ICS that does similar devices, but work on PCI bus, and they're $8,000 for the in board and $8,000 for the out board. So this is both for $300. So it's pretty much paradigm change. If anybody has more specific questions about that, we can talk about that.
Come on by. We're pretty much located in the crypto village cypherpunk tent in North Plains. We're calling this thing the Universal Software Radio Peripheral. Because we needed some short name, we call it the SIRP. And for those of you who are interested in sort of the politics of this kind of thing, is that I know that it's true in the US and I know that it's true in Europe, is that there are sometimes restrictions on what you can receive and or transmit. So the solution that we're designing with this board was a board that really solves one of the hard parts, which is really getting the analog data in and out of your PC in a quick way and solving it once. Then people are free to build whatever kind of these RF transverters out front. You can build a receiver for RF down converter. And those are actually still in the hobbyist range. So you can still build those things by hand for single band applications, not too tricky. It's a little trickier to build boards that run at 120 megahertz by hand, so we thought we'd try to do that part with a commercial vendor so that you're free to just order things out and then go from there. Okay, how do you Okay, so this is kind of the architecture diagram. So you've got the software radio app, which is most likely GNU Radio, and that's the engine. And the application, so GNU Radio is kind of a library, and so your application would be on top of that, and most likely written in Python, actually, which is how we're doing things these days. The actual signal processing code runs in C, but the UI and tying it all together is in Python for ease of use. Now it runs on your PC, which connects by USB 2 to the board, and then the analog in and out of the board would connect to your transverter or transverters, which actually we're using that term without defining it. The ham normally is the transverter will take your IF signal, in this case a pretty low IF because it's coming out of the board, and translate up to an RF frequency and transmit it, and also receive and translate that channel back down to your lower IF frequency. So someone would have to design transverters to work with this board to do most practical things we want to do with it. But so the board is the section. Good. Okay, for demos. This is just to start. This is one of the stills from the HDTV receiver that we built. HD in the US when it's in the high definition. So there's digital television, and depending on what time of day it is, they run programming in different formats. And the best format that they run, they run a 1080i format, which is really 1,920 pixels wide by 1,088 pixels tall. So it's really about 4 times as many pixels as most people have on a display. we're going to start with the world's most expensive FM receiver. And yeah. I don't know what else. Yeah, good plan. All right, that's a great level. Okay, so just before we do that, we'll go back to our preview of the track. This is what we were running earlier. So we see a couple of. Yeah, okay. We're going to play with the hardware.
Okay, so what you're actually seeing here, we have an antenna up here, which goes into this, this is the transverter we're using. It just kind of, this one receives everything from about 50 to 800 and something megahertz. And you can translate that down to a lower IF frequency of about 5 megahertz. And then that goes into a PCI card that's in the computer, which does A to D conversion. And this one does it at 20 megasamples per second, 12 bits, and costs about $1,200. So we're going to be replacing that with our USRP platform. But for now, that's what we're seeing.
So now we're going to turn. Those are radio stations. Which radio station? The two spikes. That one right there and probably the one right there. That's probably one down there too, but it's probably a little scratchy. Okay, so here's.
The software is taking a signal in at 20 megasamples per second here and processing it for what you're going to see. So,
you want to bring this up? I got my volume up. So anyway, trust me with music. Okay, so that's a single channel. I'm going to turn it down so we can talk for a minute. And, Sure. Yeah. So the thing you can't see on the top because the auto scaling isn't working is the result of the initial channel selection fixed in the Python code. Okay. The next thing now, for those of you who have actually kind of messed with FM radio, commercial broadcast radio, it turns out that this spike right here is at 19 kilohertz. This is what they call a pilot tone for the stereo information. So everything to the left is the left plus the right channel. And then everything from here over is the left minus the right channel. And then this stuff out here is probably like RDS carrier or something like that. Some sub-carrier information depending on the channel to run. This over here is really the same thing, only it's been decimated a little. It's been decimated and reduced. So this window over here is pretty much a filtered version of this part that just goes from here to that spike.
That's a spectrum display of what you're hearing on the sound card.
Okay. Okay, so now we're going to go with the world's most expensive two radios. We're really gluttons for punishment here. Okay, so what we got here is we got one channel coming out one speaker, one radio station, and coming out the other channel is the other radio station. Now there's really, you can do this. We always try to find things like for religious programming and rock and roll. It's a good contrast. But anyway, this is very driving myself crazy with it. But really, what we want to demonstrate is really with being two in one place, we have a wide band system. You can select multiple signals out of it all at the same time. There's great applications for this. If you wanted to, for example, we're building a paging receiver or any kind of trunking radio system. You want to, you're building a system. You want to watch a few paging channels and then some traffic channels. You can do them all at the same time. And if you were thinking about like a scanner application, spectrum monitoring, you get to see them all the time. It's not like you have to go between them. If you're missing the one you're scanning along, this just gets them all. And it's of course just limited by the framing you have and by the speed of your analog computer. Anyway, the software doesn't really care in one sense. We just try to build a general purpose toolkit that can be put to all kinds of uses.
Yeah, and you can also transmit multiple signals at once. We've shown with 2 FM channels, but really there's no limit, except that we only have 2 audio outputs, but it's kind of, you can make a 4-loop instantiating many supplies.
Okay.
Yes. So it's interesting, for example, the FM radio, most of the processing power that's used, and you can do this on like a computer, it's on a machine pretty easily. But most of the processing power used for the FM demo, for example, is used in the front end filter in the first stage. And actually that's shared on all of the channels. So if so your first one might use 30, 40, 50% of your CPU, but the additional ones use only another percent or 2 because they're sharing that functionality. So you could do a lot of stations for the same CPU load. You don't need that's why I said a 2 gigahertz CPU.
And the other thing is that this first, like selecting your narrowband channel out of the wideband input. So let's say you got 20 megahertz in this case, and you want to get it down to about 400 kilohertz. That's a relatively expensive operation of any software. And you can imagine you've got 60 million samples per second. It's really wide. You want to pull out a, say, 30 kilohertz wide channel. You can do that all in software, but that specific piece is the piece that we put in the FPGA as the first cut. Because it is the computationally most expensive piece, and it's for the most part independent of whatever your modulation strategy is. There may be some slight difference in the filter that's required, but mostly we can try it.
You also need to do that ahead of the USB bus because that's kind of the bottleneck. You want to reduce your data with it.
By the way, about the FPGA again, did you plan to make the FPGA reconfigure
Oh, yeah. Yeah, let me ask you, the question is reconfigure when I stop it and I reload it completely, or do you want to reconfigure a portion of it at a time? We do not reconfigure.
Like you said, there are some operations which are very expensive and should be done in a different stage.
Right.
And there are other ones like tunes and stuff.
Okay.
My question is, do you plan with this keyboard or whatever to reconfigure it by actually running and receiving but in the loop and saying, okay, I want this application, and when you have like many computational problems in the runtime for don't care about that.
Okay.
Wide spectrum
Okay, so there's reconfiguration on a number of levels, I guess you could say. There's actually no non-volatile storage on the board. Everything is downloaded over USB. So you program the FPGA over USB. So that's the first level. The second level is that, okay, so with the FPGAs, the way they are is that you can't reprogram part of them. You have to basically shut it down, reload the whole thing, and do that.
Unless you spend a lot of money on a really big, fast, expensive part.
Yeah, which would be able to sell for $300.
possible we program
Right.
all the stuff,
Right.
only shades.
Right, and so, okay, right, so the idea is that for things, there would be several basic applications, and so for each one you would send the appropriate FPGA code to the board. And then if you want to change things like number of channels, center frequency, decimation ratios, bit rates, all that stuff, that you don't actually have to reprogram the FPGA, you just kind of send it a command, and it can change that on the fly. So it's kind of like it has some boxes in there. So you can't put everything in the FPGA because it's a limited size, but we put enough in there that you can do pretty much everything without sending a new bit stream.
Just like my main interest in this discussion is interface again, or
Yes, this everything, absolutely.
The question is this going to be open?
Yes, every bit of this is open. Now, we advise people not to be changing FPGA configuration themselves because if you do it wrong, you can blow boards up and things like that. But you will be able to if you wish.
We give you everything you need, and it's a very flexible piece of hardware. We want to ship it with the standard configuration that we believe isn't going to damage the board. But these things, just to get an idea of this, these things you can turn inputs into outputs. And you can imagine you've got outputs driving outputs, you're creating shorts. So it's like mad. And you turn these $300 boards into like paperweights. So we give you all the rope to hang this stuff. We suggest you know what you're doing, you be really careful, if you let the smoke out, the vendor's going to be really happy to sell you another board, and you're welcome to go down like that. Okay, here's the same sort of... No, you can't go ahead. I'm not going to stop it. This is not happening. This is the same code we used to look at, except this is a pipeline version of it. This is a single channel FM receiver. And how do we think about this? There's a couple of ways to think about the game plan, or how GNU Radio plays together. And the first kind of thinking about it is we have a set of blocks, a set of basic signal processing modules. And you can think of them like you have an infinitely long stream of data coming into them of a particular type, and then you have multiple streams coming into them of a particular type. They grind on it and they produce some outputs. So a simple example would be, you could say an interface to an analog to digital converter has no inputs and produces a stream of samples itself. The flip side is the same, which is a digital to analog converter, which takes some kind of an infinitely long stream of 16-bit integers or complex numbers depending on your preference, and eats those and magically sends them out to the hardware. And then you've got blocks in between. And these blocks in between could be sort of standard filtering operations, these FIR, finite impulse response filters. They could be phase lock loops implemented in software. It's too much anything you can imagine you can do in there. So you've got a set of primitive blocks that have a signature. They take a particular number of streams of particular types of inputs and they produce it out. So we instantiate a few of these up front here in this code. And I'm an X and X user, so can you read any of this? But just semi-readable? Okay, good, so let me get it all seen. All the source code is online. The easy way to find this stuff is to go to Google and punch GNU Radio, 2 words, or 1 word, and hit the I'm feeling lucky button. And you'll be lucky. So there's a web page here, there's a mailing list, there's all the source code. There's tarbles there, and there's also access to the CBS repository. So then what we do is we build some modules here. So starting right here, we say, okay, we say, make me a GRMC4020 source. Well, okay, lovely name. But anyway, that is the source module that knows how to talk to that ADD card. And of course, one can think, well, layer of abstraction without picking an ADD module. This happens to give you the right one I need. And then we say, okay, fix the offset in the thing. It turns out that this board produces not 2's complement number, but sort of offset binary. So we need to subtract out the offset. And then we want to build a low-pass filter. So this particular function call is actually a filter design thing that happens once when you instantiate the thing. So we get a set of channel coefficients, these are taps, FIR taps. And then I say, okay, go build me the actual filtering module using the taps I just cooked up. And this one is the frequency translating FIR filter. which is its main job, is to extract the narrowband signal from the wideband. Then the actual FM demodulation operation is this quadruped demodulator, which we might want to look at in C++ just to give you an idea. It's only about 4 lines of code. And some more filters. So I'm going to instantiate a few modules, and here's the sync. And the sync is a GR audio sync. Okay, so it's where I'm recording my sound card. So I've got some primitive modules instantiated, but they're not connected to each other. So then I say, okay, create me a flow graph. And the flow graph can be the container that wires everything together. So then you're going to say, connect. So I connect the source to the offset fixer, the channel filter, the demod, the audio filter, the final sync. And then that function returns that flow graph. So the idea here is I've got this flow graph, and I don't really care how it gets executed as long as it goes fast. So down here, then you say, okay, this is a call that functions off, build me the graph, and then start the graph. So starting the graph goes off and does whatever it takes and returns immediately. So it forks off some threads. So the game plan is it will run, twice as fast on a dual processor system. Currently it doesn't, but that's the game plan, and it's an interface that's already playing. So you just say, go run with it. If in fact part of these modules are on your FPGA, then they get load the right code down to the FPGA, and just magically everything is running. And then you've got whatever, if you've got GUI or something, it's running over here, your main load for your GUI. And that's the whole thing. So that's a single channel FM receiver. A plug for Swig. Swig is an excellent tool for those of you who ever write bunches of C or C++ code and then want to get it stuck into Perl or Python or Scheme or anything. Really wonderful tool, really easy to use. Swig, swig.org. Highly recommend. Let's see what else we got here. The next demo is we're going to play now the HDTV, the demodulated HDTV signal. So this was how we gather this, because right now this is CompUser. Give you an idea here. So we got 20 million samples per second coming in. They're 12-bit samples. We write them to disk at 40 megabytes a second. So you got a pretty hefty stream coming. In fact, you're going to need 2 drives with some kind of RAID stripe event. You can actually make this happen. So you want to record your half-hour TV show at 40 megabytes a second to 72 gigabytes. Okay, then what you're going to do is you're going to throw it at the receiver model, because the receiver doesn't currently run in real time. And right now it actually takes about 30 times longer than real time. So if you had a 30-minute show, it takes 15 hours to grind it. So the input is, we think this is fixable. We have a goal this year to run out of time, but there's a clock or a calendar time. The goal is to run this in real time sometime this year on some big hobby SMP machine sometime. Talk to our friends at Sun and say we'd like to borrow 64 processors for just a while. So there's improvements in algorithms. There's certainly room to maneuver, but I'll tell you, when you've got a 256 tap equalizer, you take something, you take a 10.76 million symbols per second, and we've got really fast FIR code, but that's still multiplied, you've got numbers that are like 256 times 10 million, and that's one stage in the pipeline. So yeah, we're all for algorithm improvements, and we can say we pick up a factor of 5. 10. We're really happy it's working right now. There's lots of room to maneuver. There's different algorithms you can use for pieces of it. You can put some of them maybe on the FPGA. So then what we did is we recorded it to disk, and then we ran it through the demodulator. And the output of the demodulator, so the input is samples. The output of the demodulator is an MPEG transport stream. And so for those of you that don't know, MPEG's got a couple different layers in it. And the bottom layer is kind of is the one that's designed for the transport layer. has fixed length packets. So there are 188 byte packets. They start with hex 47 and all that. Built on top of that, there's a bunch of program information, the audio channels, the video, possible multiple programs all mixed on top of that. Our receiver doesn't look at any of that stuff. What we produce is just a transport stream outbound. So what we're going to play back here is one of these transport streams that we're recording. And we apologize before we show the thing. We're very thankful that we're able to borrow the computer that we have here. It doesn't have enough guts to run the player in full speed, so it's kind of jaggy. And for some reason, there's no audio, which is some software problem. I'm not sure. So we'll show it to you, sort of the full screen, and we can clip it down a little bit, you actually see it running. The episode happens to be some episodes in long order. I'll pan around it and get an idea of really how many pixels there are on these things. It's pretty amazing. I'm really looking forward to them. Really, in the U.S. right now, they're selling these quote wide, these HDTV rated monitors, the flat panels, but most of them don't have all the pixels on them. Most of them are only about 7.5 or something, like 1920. I'm looking forward to the affordable wall flat panel company. Yeah, with all the pixels, please.
Also, the fact that this computer really can't just play the already demodulated thing back in real time should tell you something about how complex this, how much processing goes into actually producing this.
So, just to, again, while we continue to apologize, just the MPEG stream itself is 20 million bits per second is its range. So that's the channel that it comes down. So this isn't like your DVD. Anyway, here we go. Alright. Okay, sorry about the video. Here's that's the full width. We're seeing everything there is to see, but we're only really getting about a quarter of the pixels because it's being scaled to fit this 1K by 768. The real image is 1920. If I go back to this, you can sort of get a little better idea of how the graph. Yeah, we're getting a corner of the. There's kind of we're not losing any pixels. Well, we're seeing each pixel represented one for one. We're clipping everything off. So it gives you an idea of the kind of detail that's really available in this stuff. Excuse me? Flicker? Yeah, there are artifacts. They're in there. It's like you watch, sports on the satellite TV. You get a different set of problems than you get on your analog televisions. They're there. Of course, we've got things zoomed in so you get to see all the fun stuff. So, this is future. These aren't necessarily that I'm going to do or Matt's going to do, but these are all things that are definitely possible within the radio framework. So, we're looking for people who are interested in playing in this arena. We think that you guys are the prime candidates, particularly for things like Tetra, which we don't have. We don't have any of those. So, anyway, there's some things we'd love to have done. We think they're like doable. Some of them have like more difficult stars next to them than others, but the Tetra, it's QPSK, which is a piece of it. All the ham radio roads. Mostly the recent with your reset done. We've been the suicide people going after the really hard stuff, building infrastructure. Let's do digital television. GPS is another thing. We found an open source implementation of GPS. The whole area of ad hoc mesh networks is a lot of academics interested in that. People that we talk to about it, universities are very excited about the board that we've shown you. You might must have multiple input, multiple output, smart antennas. You can think about building killer direction finding stuff with this, or being able to do spatial division of multiple transmitter receivers. Again, whatever you want. We're trying to provide a toolbox to build whatever you want. And of course, developers want it. There's a mailing list. GNU Radio is available with the item locking button. And that's what we got. So we'll take questions either now or also later on. And then we're in the CypherPunk's tent, and we'll do more demos and answer questions about that. Any more questions now?
I got one.
Can you get to the mic, please?
Actually, too, how soon are you going to have some kind of functional, are you planning on doing a functional packet radio application?
Functional?
Packet radio application?
I don't think it's not on my to-do list.
Okay.
Okay, so if you're interested in this, and you ask a question, it makes you a prime candidate for this.
My other question is scientific analysis. Have you seen the application sweep or GL waves where they go into, sweep is a music editing, but it also does a pretty good job going into a waveform, and GL waves actually shows a 3D waveform with an EM wave or any other kind of wave. Have you looked at scientific applications? By that I mean just more analysis of the actual EM wave.
We haven't particularly, we've used a bunch of the other common tools when we're developing, when we're working on some of these things. We use Octave, for example, for looking at stuff. But not that particular one. Thanks for the suggestion. Good. Other questions? Thank you to our microphone runner. Next one. Yeah, guaranteed. We're gonna
I want to talk about the GPS software after Garmin 12 and got connection to a computer. Does it is enough to pick up the signal? Does it Garmin 12 GPS will give me the signal? I will be able to use it in the computer, or do I have another connection or adapter in between?
Oh, okay. Yeah, so this would, you wouldn't have to go out and buy your Garmin. You would have, one of these boards again, and you have an RF front end that just receives that, puts it into the board, and then comes over the USB, and all the processing would be done in the PC to do that. So you would be, again, this would be the most expensive GPS receiver. Although actually, the military does spend a lot of years, but the most expensive consumer GPS receiver.
Good. Any other questions on this side of the room?
How much is the actual RF module gonna cost for say the 2.4 gigahertz range?
So that would depend on whoever actually makes the RF module for that. We may at some point make our own RF modules, but really, we concentrate on the IF part.
You really don't want to be we don't want to be in the hardware business.
Yeah.
We're not in the hardware business. We reluctantly, when we built this board, we found someone to design the board and found someone to build it for us. We're looking for partners of some kind who want to build whatever we want to build. We think people we've been after are like applications engineers for some of those people like Max and that we design the right parts that you want on the front end. So we're going, hey, why don't you apps guys build some boards?
Yeah, and I should say that, for example, the 2.4 gigahertz band, which is, of course, very popular, there are some really good chips there where you have one chip for the transmit, one chip for the receive, a couple caps, and some filters, and that would be it. And this would be a very simple board that you could just plug onto this. And so, I have ideas. If anyone's interested in actually, especially in the hangouts, interested in actually making one of those, I'd love to talk to you.
Great. And that?
What kind of legal trouble do you expect with this?
No, really, I have spoken to people at the FCC, which is the Federal Communications Commission, and they're not. There's like two camps. There's like the engineering side, which tends to actually understand physics and science and what radio is really all about, and then there's the political side. So now the political side understands things like money and there's not enough spectrum. So they start to listen to the engineering side. So the FCC, and I know that it's true in Japan also, I wouldn't be surprised to find that it's true here, but I can't speak about that, is that there's a perception that there isn't enough spectrum to go around, or that it's being misused or something like that. So the FCC has been looking for ways to make better use of the spectrum. They're investigating a bunch of policy issues, but also different economic models with them. Some of them, some in the United States, television stations really don't pay anything for their huge allocations. Although the cellular companies did. I mean, it's a historical artifact. And then we've got certain unlicensed pieces of the spectrum of 2.4, 5 gigahertz, and 902 and 928. So there's a whole public policy discussion that's being held, and it's being held in major universities. It's being held in Washington about law school professor Larry Russell hosted one a while back. They're really looking at these issues. What's the right way to manage this? And on the technical side, there's a bunch of people, probably spirited by David Reed, at MIT and now at HP also, calling into question this whole idea, is there such a thing as a scarcity? Because he's kind of saying, well, can you ever imagine running out of green? And they say, we're out of the color green. Well, no, the color green is still there. So there's a whole set of questions. But to get back to the technical aspect, as a result of this, the FCC is really looking for technical solutions that innovate and allow them to make better use of the spectrum, and at the same time handle the reality for our legacy users in the spectrum. They installed point-to-point microwave users, the broadcasters, the cell phone folks, and they come up with some pretty clever ideas. This idea that you have an easement where as long as I was operating below kind of noise of the other guy, you shouldn't care. There's also the idea of building these what they're called cognitive radios or smart radios that have the ability to kind of look around and sniff. And either they know geographically where you are, they can consult the database, or they just sniff around and say what's going on. Because if you look at it, if you're in a rural situation, there's really no reason you shouldn't be able to run more power. You don't want to get from A to B, not in the middle of nowhere, and nobody's saying anything, why can't I run? So, and the thing about all that is they see that software radio is the enabling tool for them. So in general, they're big on software radio. They got some concerns about open source, or free software radio, because my God, people could do anything with that. But they see the reality of the situation is that that's where innovation is occurring, and that it's a lot of this conversation on the regulatory side looks an awful lot like the conversations that we had about cryptography export. There are some of the same fundamental issues relating to First Amendment U.S., First Amendment protection of speech, and the acknowledgement in several court cases that, in fact, software is speech. So we don't go out of our way looking for trouble. We stay in communication with the people. And we don't transmit illegally, and we do our part.
Yeah, it should be said that using a tool like this, you could get yourself into trouble by transmitting on some rich person's frequencies. But that is not, we don't, it's kind of a personal responsibility thing. And so, yes, there's a lot you can do with it that's illegal, but the concept of software radio itself is not illegal.
I'm sorry, quite the conference that was supported by the military and most of the commercial radio, software-defined radios that now really built with military applications and so on. One question related to that is the SDR4 is a software common architecture
Yeah, it's hideous.
I know. They can use it.
We don't, personally, I'll tell you, I've looked at it, I've talked to people who got paid lots of money to implement it, and as
It's not fun.
well, it's a giant, nasty corporate interface to something that probably doesn't really fit a nasty corporate interface. And people that are building commercial radios in the military marketplace, that's what they're going to do. But that's their money. But it doesn't mean it's the right answer. It means the right answer is to make money selling these radios to the military. We've looked at it because of free implementation. From our point of view, it doesn't, the granularity of that solution is too coarse. It's too coarse. It's like hideous.
I agree. I think it.
I'm sorry. About the receiver transmitter, you said that it's probably going to be in the shops in like 2 months or something like that. What kind of shops will you look for? Do I have to dig that from somewhere, or is it going to be available widely in different countries?
Are you referring to the board we've been holding up?
Yeah.
We're not publicly announcing the vendor who you're going to buy it from yet because we're really kind of waiting around and teasing you right now. We've tried to have a deal with them not to open our mouths and say what it is until everybody agrees it's going to go on. But it'll be available. This is a commercial board vendor. I'm sure they'll find a way to sell it to you. But yeah, on the web, they've got a web presence. If you sign up for the GNU Radio mailing list, that'll be the first place that there's, we'll tell you where to go and buy it. Yeah.
Okay, another comment. Not that you are using general purpose PC for radio stuff. The problems with legalese might be also the hacking part. So when it's general purpose PC, people hack into it and might start transmitting stuff to the radio waves. It's not only the person who owns the computer, perhaps, but that's not, of course, it's not your problem, but just something that has to be considered.
It's a good question.
It does keep the FCC up at night that when this ends up in cell phones, that somebody will hack into cell phones and make them all transmit something wrong. But even more direct is if it's on your computer, you whatever your computer getting hacked, you could do something totally illegal with it, right? And so, yeah, there's all, you could kill somebody with a spoon too, but we still have spoons, right? I think that's, although some people would stop you, I do think that's where some people would like it to head.
For these devices, you can import radio transmitters quite cheaply for about $300. You can locate a radio transmitter. So it can be used to find unlicensed radio transmitters or pirates or other.
Yes, this actually would make a great tool for enforcement of if somebody else is breaking the rules, you can find it really quickly because we're going to have 4 inputs and with 4 antennas you can do direction finding.
And there's a piece, this particular argument is one that we've been trying to persuade the FCC that instead of banning spoons, because sometimes somebody will kill someone with a spoon, that maybe you should go after the people that are killing people with spoons. So they're not really wrapping their head around this, but we keep pointing out that look, these things, you can build some really killer direction finding equipment, and the truth is, we can't find them. They must not be too big of a problem. And again, it's a culture class. You got an institution whose job is to make regulations and enforce them, and they get all paranoid about stuff. But I keep saying, putting them on engineering hat, well, you talk about these hypothetical situations, tell me a real one that's occurred, what was the consequence, how did you solve the problem, and let's talk. Don't give me this disaster scenario, let's talk what's real and how to fix it. Sure. You can get a mic back to Senator for yourself.
A lot of enforcement, at least in countries with evidence of who transmits where, is actually enforced through possession rules on the transmitters. You are not allowed to possess transmitters of a certain type over a certain power that can transmit certain modulations on certain bands. All of that, of course, goes out the window. If you have these wide band transmitters and everything else in software, it means any goes out. And you can't really enforce possession of the software, it's going to be encrypted or whatever, so it does change that.
Yeah, well, that's definitely, in the US too, that they regulate in that manner where, you know, for example, if you buy a scanner, it has to have cell phone frequencies blocked, even though it's very easy to unblock. So, that's part of the reason why this is, you know, we're not really making RF sections. Like if we made an RF section that would transmit on cell phone bands or even receive on cell phone bands, I'm sure we'd be getting a call. So, again, if you make the RF sections, you know, again, these are silly rules, but this is how they tend to be. So, part of the reason why we're leaving the RF sections up to other people is for that reason. So they can make the ones that they're allowed to be using and handle their own enforcement.
Seth?
There is another application which, for political reasons, we would like it if someone would like to implement to complement the terrestrial ATSC VSD demodulator. We would love to see a QAM, SCPE QAM demodulator for a digital cable. That would be really great and helpful politically if anyone is eager to do that. I'm not sure if the SCPE QAM is used outside of the US, so there might not be a huge incentive.
QAM in general is used everywhere for all kinds of things, so it would be a great thing to do. So Seth's talking about cable, is this modulation strategy using cable, plus the dock system. I don't know if that's what they're using in Europe or not. But anyhow, we can provide samples if anyone's interested when we work. Good, thanks.
Then you receive all kinds of digital TV. So it would be cool.
Well, but you maybe see the bit stream and it's all got conditional access, so you don't have to see anything, but it doesn't need the receiver.
The FCC is still in the proceeding where they're going to decide under what circumstances they can put conditional access on the cable. So it's not a closed story yet. It may or may not be conditional access for certain things.
Okay. Good. Any questions? Anyone else tonight?
Well, the PCB design, the open source tool, is that proprietary type of manual manufacturing?
The schematics are open source. You free to take a look at them. But it's kind of like the PCB thing is an escrow if the company stops making them. We're making them. I promise you, the cheapest way to build one of these is to buy it from these people. But we'll be shipping the schematics.
So it won't be a problem for other companies to just get a similar board.
To build a single board or
Get a similar board so that there's
Yeah, it would entail the same startup costs of laying out the board together if this company went through with it. That will be possible.
Yeah,
That won't be your quickest route to
this is more than earlier, but there are people that have been corresponding with me that are also looking at building a receiver board, kind of transceiver board, kind of like this one that's the narrowband and the 0.60 megahertz board, but they're thinking about doing it initially with 100 megabit Ethernet. They didn't like USB. I think really the problem is they didn't understand USB. I said, it's really simple. Here's what they're and I said, great, go build it. So there, I expect to see, probably sometime in the next 6 months is that someone's going to have, another thing. And again, from our point of view as really builders of software, we welcome more ways to get the samples in and out. We've talked to these people. We said, look, let us know, publish the specs, and we'll code them up or help you code them up. Good. Anything else coming up? Okay, last chance. Anything else? All right, well, I want to thank you all for your attention. It's been great being able to talk about this stuff, and we're mailing list. We've got a fair amount of people and traffic on it, and we have the web page, and there's a weekly link to off of the web page. The FAQs are off of there, and again, we'll be around through Sunday, and we'd love to talk to you. Thank you very much.